Very good morning, one and all. So in the last class, we have initiated the pulse digital modulation technique. So second type of pulse digital modulation technique is delta modulation, and we have initiated that, and we discussed its drawbacks. So in the today's session, we can discuss the SNR calculation for the delta modulation system. Okay. So before going to noise evaluation, prior to that, let us discuss key points what we studied in the earlier class. Okay, so in the last class we discussed the main advantages of DM delta modulation as it reduces the channel bandwidth. Okay, it reduces the channel bandwidth required to transmit the bit sequence or the binary sequence, or you can call it as coded code signal. Okay, so how can you do that? How can you reduce the channel bandwidth? By reducing the signaling rate, and by reducing the, so upon reducing the signaling rate, you can reduce the transmission bandwidth, because there exists a relation between signaling rate R and the transmission bandwidth as R by 2, where signaling rate is defined as the product of N and Fs. So what is the main drawback of PCM? PCM transmits all the redundant bits, or you can say all the number of bits present in each and every sample. Okay, so to overcome that problem, delta modulation, what it will do, it will transmit only 1 bit per sample. Okay, instead of the traditional quantizer and encoding section, this delta modulation makes use of 1 bit quantizer, where this 1 bit quantizer transmits only 1 bit per sample, only 1 bit per sample. And the output of the 1 bit quantizer is a staircase waveform. We represented that as U of NTS. Okay, and that staircase waveform has fixed step size. Already we discussed. It has fixed step size variation, that is of delta. And that staircase waveform step size will vary in accordance with the magnitude of x of t. Okay, what we did there, we have compared the present sample magnitude of x of t with the past sample magnitude of x of t. Okay, and if the magnitude of x of t goes on increasing, our staircase waveform will also increase with a step size of plus delta. Okay, for example, if the magnitude of x of t, present sample value, decreases, our u of t will also decrease by a step size of delta. So what is the step size of the staircase waveform u of t? It is of plus delta and minus delta. See, always remember here the staircase waveform has a deviation of plus delta and minus delta. Okay, so that's why here the step size is fixed. So that's why you can also call the delta modulation as linear delta modulation. You can also call the delta modulation as linear delta modulation. Okay, and here in the case of PCM, we have A to D conversion process is there. Okay, so we make use of sampler, quantizer and encoding section. Okay, but in the case of DM, we can simplify that circuit. We can simplify the circuit of PCM by replacing the 1 bit A to D converter. So you can replace the A to D converter just by a 1 bit quantizer. Okay, and in the feedback, an accumulator is used. In the feedback section of DM transmitter, accumulator is used. You can see that if you observe the transmitter block diagram. Please, all of you observe the transmitter block diagram. Here the input is x of NTS, that is sampled input. And that sample data is applied to the 1 bit quantizer. And how you are applying? The sampled input is compared with the past sample data. Okay, that past sample data is stored by the accumulator. Okay, so if that is the first sample, there is no need of comparison. Directly the data will be applied to the 1 bit quantizer. From second sample onwards, second sample will be compared with the first sample, and third sample will be compared with 2TS, 4TS will be compared, magnitude will be compared with 3TS magnitude. Like that, the past data is stored in the accumulator. Okay, so sample data x of NTS is compared with x cap of NTS, where x cap is the past data. So what is the resultant here? This comparator takes the difference of those two and generates the output as error E of NTS. Here we represented summer. Okay, that is a comparator actually. That comparator compares the magnitudes of present sample and past sample, and it generates E of NTS, where E of NTS is the difference between the present sample and past sample. So we represented the same in the equation 1. Okay, now, so that error E of NTS is applied to the 1-bit quantizer. This, let us assume 1-bit quantizer output be B of NTS. Why we are specifically calling as 1-bit quantizer? Because this it transmits only 1 bit per sample, only 1 bit per sample. Okay, so let the output be B of NTS. Now this B of NTS, it can be either plus delta or minus delta. What is B of NTS? The output of 1-bit quantizer can be either plus delta or minus delta. Either plus delta or minus delta. It can be plus delta when the magnitude of error, is positive. Okay, so it is minus delta when the magnitude of error is negative. When the magnitude of error will be positive? When x is greater than x cap. Okay, so when x is less than x cap, then error will be negative. When x is less than x cap, error is negative. So our B of NTS will be minus delta. Now, that B of NTS is added with the past sample magnitude, and that output is generally called as U of NTS. So what is U of NTS? U of NTS is the staircase waveform that's generated by the accumulator. So what this accumulator do? Accumulator stores the past sample values and is stored as a staircase waveform with the magnitude variation as plus delta or minus delta. Okay, now, so what is now I can say that the staircase waveform magnitude, past sample magnitude, U of n-1 TS as x cap of NTS as the past sample value. Okay, so from this you can say that U of NTS is the output of the summer and it is input to the accumulator section. Okay, so it is equals to U of n-1 TS plus B of NTS, where B of NTS is equal to plus or minus delta. The same thing we discussed in the last class. So what is B of NTS? Output of 1-bit quantizer. So how can you write in the form of expression? Delta into sine of E of NTS. When sine of E of NTS is positive, you will get plus delta. When sine is negative, you will get minus delta. So plus delta when sine will be positive, when x is greater than or equal to x cap. When x is less than x cap, sine will be negative. So you will get B of NTS as negative, minus delta. Okay, so so here there is no need of separate encoding principle as in the case of PCM. So what you will have here, whenever you get like staircase waveform is modified by plus delta, then data bit 1 will be transmitted. Okay, so data bit 0 will be transmitted when our B of staircase waveform is modified by minus delta. Okay, as an overall, the DM section input is the sample data. 1-bit quantizer, the input is sample data. Not exactly sample data, difference between the present sample and past sample value. And the difference is transmitted via 1-bit quantizer. And this 1-bit quantizer data is stored as a staircase waveform, in the accumulator section. So I can say that the accumulator data U of NTS can be related as U of n-1 TS, that is a past sample approximation, plus B of NTS, where B of NTS is equal to, what is B of NTS? Output of 1-bit quantizer. Okay, so you can rewrite B of NTS as delta sine of E of NTS, that is equals to plus or minus delta. Okay, so already we defined so many times in the last class. So when E of NTS is positive, B of NTS will be plus delta. Then data 1 will be transmitted. Okay, then it is encoded as 1. Okay, when E of NTS is negative, B of NTS is minus delta. So data 0 is transmitted. Okay, so next, this part we discussed in the receiver. The same principle is applicable in the receiving section. What that principle? The present staircase waveform is equals to past sample value or past staircase waveform plus B of NTS. What is B of NTS? The data update, that is the encoded data, or you can say the output of the quantizer. Okay. Now, what is the input to the receiving section? The encoded data. The encoded data. So, if B of NTS is equal to 1, for example, at the DM receiver section, it consists of only the accumulator section followed by low pass filter. Please observe here that there is no separate decoding section. Okay, so that's why the circuit of DM is like simple, and implementation is also easy compared to PCM. So this is all to reduce the bandwidth, to reduce the requirement of bandwidth. We are using delta modulation. Okay, so if B of NTS is 1, then accumulator, what it will do here? It will add plus delta to the past staircase waveform. What is the past staircase waveform? U of n minus 1 TS. How can you get that U of n minus 1 TS? That is stored in the accumulator. That is stored in the accumulator. This accumulator is the same one used at the transmitter section. Okay, so U of NTS plus the input signal. So when input signal B of NTS is 1, so you will get accumulator adds plus delta to the previous staircase waveform. So here you will get plus delta. So when the encoded data bit is 0, then B of NTS is minus delta. So staircase waveform is reduced by a magnitude of by a factor of minus delta. Okay. Now that present staircase waveform U of NTS is generated by the accumulator section. Now the data is applied to the low pass filter. So what this low pass filter do? This low pass filter reconstructs, or you can say that it smoothens the staircase waveform. It smoothens the staircase waveform U of NTS to generate the X of t, Okay, so we discussed all these points in the last class, and also we discussed the drawbacks of delta modulation. So what are the 2 drawbacks of delta modulation? This delta modulation is suitable for the input signal X of t with continuous variation. If X of t is a continuous variable signal, then only this DM signal is applicable. Otherwise, you have to modify you need to vary the step size value. Okay, so what are the drawbacks? One is called as low power load distortion. Second one is called as granular. It is also called as or idle noise. And this granular noise is also called as hunting. It is also called as hunting. So what we discussed regarding slow power load distortion, any one of you please respond. This is the part that we studied in the last class. So can any one of you respond and tell me what are the 2 drawbacks of delta modulation? And what is low power load distortion and what is granular noise? Any one of you please respond. G9 came. అమ్మ మనోహర్ చెప్పు నువ్వు lateral entries
ma'am.
చెప్పమ్మా. yesterday you said na Two types of delta modulate. What are the two drawbacks of delta modulation?
Startup error and
Slow
hunting.
overload distortion and granular noise.
Yes,
What
ma'am.
is slope overload distortion?
If x of t is very high, ma'am,
When the slope of x of t
x
is
of t is
very
very
high compared to slope of u of
u of
t.
t. The u of
Okay.
t cannot able to follow the x of t, ma'am.
Yes, cannot able to approximate the x of t.
Yes.
So there exists a lot of difference between the slopes of x of t and slope of u of t.
To
So this
avoid
kind to avoid slope overload, what you need to do?
increase the step size, ma'am. Delta.
Yes, very good, very good. Tell me about granular noise.
If a slope of x of t is very slow and flat,
Yes,
the u of t is oscillating, ma'am.
just oscillates around the input signal with a magnitude of plus or minus delta. So the
Delta.
error between the input and approximated signal at the time is called as granular noise. Okay. So how
Uh,
can you overcome this granular noise?
to decrease the step size, ma'am.
Yes.
Decrease.
So what is the drawback of linear delta modulation? This is mainly due to the uniform step size. Okay. So for slope to avoid slope overload distortion, please increase the value of delta so that u of t can approximate x of t. And during when slope of x of t or when x of t is almost all flat or when you have minute amplitude variations of x of t, then please reduce the step size so that our waveform, the u of t can be able to follow properly the x of t. Okay. So the thing that you should do here is please make use of variable step size in order to overcome these two drawbacks. So because we have this many drawbacks in the case of traditional delta modulation or linear delta modulation, here SNR is poor compared to PCM. So what is the main drawback of delta modulation due to these two errors? One is main drawback is its SNR will reduce. So even though you are reducing the channel bandwidth, that is the positive point, and the negative point here is SNR will reduce because of this kind of errors. So because x of t we cannot expect that slope is more at some instant, and sometimes it may be flat. Okay, so whenever this kind of case, this kind of things happen for the x of t magnitude, so automatically our u of t staircase waveform cannot approximate x of t. So the signal to noise ratio is poor at that case. So delta modulation has like poor SNR compared to our PCM. Okay, but what is the advantage regarding delta modulation? We can reduce the bandwidth. Okay, now let us go to the next slide. See, I think up to this point we studied in the last class. Now let us go through the noise evaluation. Okay, so let us see the condition to overcome the slope overload distortion. So already we said what is the slope overload error? It occurs when the slope of message signal or x of t is very high compared to slope of u of t, compared to the slope of the staircase waveform. So how can you overcome that problem? If we maintain the slope of like x of t as less than the slope of u of t, you can overcome this problem. Okay. Now to generate the condition, let us go through the mathematical analysis. Please observe the same figure what we represented x of t Okay, sorry for the disturbance. Okay, some signal problem. Okay, so let us discuss the condition to overcome the slope overload error. Okay, so what is the input signal? Let us assume x of t as am sine 2 pi fmt. Okay, let us assume the input signal as a sinusoidal signal, and please let us sample the input signal x of t at ts intervals. at Ts intervals, let us sample the x of t. Okay. Now, what this delta modulation will do? Delta modulation generates the, we already discussed, generates the staircase waveform. Okay, that let us assume the staircase waveform as, let us represent okay ma, sorry. Okay, so please let us take x of t as am sin 2 pi fmt. Okay, so and let us assume that it is sampled at Ts regular intervals. Ts regular intervals. So what is the slope of x of t? What is the slope of x of t? Dx of t by dt. Ma, what is the slope of x of t? Dx of t by dt. Okay, so what is x of t? Am sin 2 pi fmt. And now please tell me what is the slope of u of t? What is the slope of u of t? Slope of u of t is change in the y-axis by change in the x-axis. Change in the y-axis for u of t. Please observe the staircase waveform in this figure. Observe chestunara. Please observe the u of t waveform. What is the change in the y-axis? Already we know that it has linear stepsize variation of delta. So slope of u of t is change in the y-axis, that is u of t, change in u of t in the y-axis, that is delta, divided by change in the x-axis, that is Ts, because the signal is sampled at Ts intervals. So what is the slope of u of t here? Slope of u of t is change in the y-axis by change in the x-axis. Change in the y-axis of u of t is step size. Okay, that is delta. That can be either plus delta or minus delta. But delta is fixed in delta modulation. The step size is fixed in delta modulation divided by change in the sampling interval, change in the x-axis, that is Ts. Okay, so slope is equal to delta by Ts. What is slope? Slope equals to delta by Ts. So this derivation is very important for your examination. Please derive the expression or derive the condition to overcome the slope overload error. Okay, so what is the maximum slope of u of t? The maximum slope of u of t is change in the y-axis of u of t divided by change in x-axis, that is delta by Ts. Please remember this expression. Okay, let us move to the next slide to calculate the slope of x of t. What is the slope of x of t? Slope of x of t is dx of t by dt. Dx of t by dt. Okay, so because x of t signal magnitude varies with respect to time. So take the change in the magnitude divided by with respect to time. Okay, so maximum of d by dt x of t, it is greater than delta by Ts. Delta by Ts. Is this PPT visible? Ma, G5 kept to be a message that PPT is not visible. Now is this visible or not? One of you please respond. Is PPT visible or not?
No, ma'am.
PPT is not visible. So any other student respond?
Visible, ma'am.
I think maybe signal problem from your side. Okay. So now it is, now I have no problem from my side. Okay. Okay, you can wait. And let us go to the condition to overcome the slope overload distortion. Okay. So what is the, when slope overload distortion will occur? Slope overload distortion will occur when the slope of x of t is greater than the slope of u of t. Okay, so what is the slope of x of t? Dx of t by dt. If it is greater than the slope of u of t, that is delta by Ts, if it is greater than delta by Ts, then slope overload distortion will arise. Okay, Please calculate dx of t by dt. We already assumed x of t as am sin 2 pi fmt. Okay, please take the derivative for the left hand side part. It is greater than delta by ts. It is greater than slope of slope of u of t. What is slope of u of t? It is delta by ts. Delta by ts. So please calculate the derivative of the left hand side part, that is dx of t by dt. So it will be am 2 pi fm sin, take the derivative, so you will get cos 2 pi fmt. You are taking the magnitude for that, so magnitude of that, and you are going to calculate the maximum of the magnitude or the slope of what is the maximum value of cos 2 pi fmt. Cheppandamma, what is the maximum value of cos 2 pi fmt? For cosine signal, what is the maximum magnitude? Cos theta. Any one of you, please tell me what is the maximum magnitude of cos theta. Cos theta ki maximum magnitude ఎంత ఉంటుంది? What is the maximum magnitude of cos theta? Someone of you respond.
1.
1. Yes, very good. So maximum either sinusoidal or cosine, the maximum magnitude is 1. So that's why because we are taking the magnitude, you can get cos magnitude as 1. So 2 pi am fm will be the magnitude for this maximum magnitude. Okay. So if it is greater than delta by ts, you will get slope overload error. So what is the when slope overload distortion will occur? When am is greater than delta by 2 pi fm ts, when am is greater than delta by 2 pi fm ts, okay, because you have am into 2 pi fm is greater than delta by ts. Take 2 pi fm to the right hand side, so that you will get am greater than delta by 2 pi fm ts. So slope overload distortion will occur when the amplitude, maximum amplitude of message signal is greater than delta by 2 pi fm into ts. Now, what can be the condition to avoid the slope overload distortion? So here slope overload distortion will occur when am is greater than, what is am? Maximum amplitude of message signal is greater than delta by 2 pi fm ts, where delta is the step size, fm is the maximum frequency of message signal, and ts is the sampling period. Okay. So slope overload distortion will occur when am greater than delta by 2 pi fm ts. So to avoid slope overload distortion, what is the condition? Maximum amplitude of message signal should be always less than or equal to delta by 2 pi fm ts. Delta by 2 pi fm ts. So what is the condition to overcome the slope overload error? The condition to avoid the slope overload distortion is am is less than or equal to delta by 2 pi fm ts. Please remember this equation. So we can substitute the maximum amplitude of message signal while evaluating the signal to noise ratio. Okay, so what is the next agenda? Next thing is to calculate the SNR with this magnitude. What is the maximum amplitude of message signal? It is always less than or equal to delta by 2 pi fm ts to overcome the slope overload distortion. Okay. Now, let us calculate the SNR for a DM system or delta modulation system. Okay. So what first point that we derived? What is the first point? Slope overload distortion will not occur when the maximum amplitude of input signal is actually am should be less than or equal to delta by 2 pi fm ts. Okay. Now, if am is equal to delta by 2 pi fm ts, that is the maximum amplitude of input signal, so that distortion will not occur. Okay. But if am crosses delta by 2 pi fm into ts, you will get error. You will get slope overload error. Okay, so what is the condition to avoid slope overload distortion? Ma cheppali, what is the condition to avoid slope overload distortion? AM should be less than or equal to delta by 2 pi fm into Ts. Okay, now what is the maximum amplitude of input signal so that distortion will not arise? AM is equal to delta into 2 pi fm into Ts. Please take that equation as 1. Please take that equation as 1. Okay, now already we know that in PCM we calculated the SNR. So almost all you follow the same procedure. See how we calculated the SNR for PCM system. First we took the, we calculated the noise power and then we calculated the signal power. And here because we have already signal with your hand, let us calculate the signal power first and then we can calculate the noise power, and by taking the ratio of normalized signal power to normalized noise power, you can calculate the SNR. Okay, so what you can do here, first let us calculate the signal power. So what is signal power? For the signal x of t, what is the power? Power is defined as ratio of mean square value. Okay, mean square value of the RMS value, RMS voltage square divided by the normalized resistance. For normalized resistance, R you can take it as 1 ohm. Okay, but what is VRMS? VRMS is the maximum voltage divided by root 2 because that is the voltage in RMS. Okay, so AM by root 2 whole square divided by R. So we did the same procedure in PCM. So AM square by 2R vastundi. So if you assume R as 1 ohm, you will get AM square by 2. AM square by 2. Now how can you overcome the slope overload distortion? What is the condition to overcome the slope overload distortion? We have maximum amplitude of message signal AM as delta by 2 pi fm into Ts. Take it as equation 1. Now please substitute the maximum amplitude of message signal in the signal power expression. What is the general signal power expression with the maximum amplitude of AM? What is the general expression for signal power with the maximum amplitude of AM? It is equals to AM square by 2R. For normalized resistance, take R as 1 ohm. Okay, so then our signal power P will be delta square by 8 pi square fm square Ts square. Because what you did here, just we substituted the value of maximum power P as AM square by 2 and substitute AM value from the expression 1. So if you substitute like that, you will get it as delta square by AM square kada. So please take the AM square as delta square by 2 pi fm whole square divided by T square divided by 2. So that's why 2 into 2 square, you will get 8 in the denominator. So delta square by 8 pi square fm square Ts square. Please take that as equation 2. So now you got the normalized signal power. So how you got? Delta square by 8 pi square fm square Ts square. Why you took AM as delta by 2 pi fm Ts? To overcome the slope overload distortion. Okay, from this slide you calculated the signal power. Now let us go to the next slide to calculate the noise power. So how can you calculate the noise power? Already we know that what is the quantization error? So the quantization error range is from, so can any one of you tell me what is the quantization error range in the case of PCM? One of you please respond and tell me what is the range of quantization error in the case of PCM. Any one of you kindly respond and tell me what is the range of quantization error in the case of PCM system. Ma cheppali. What is the range of quantization error in the case of PCM system? G0? G0 is there?
Yes, ma'am.
Can you tell me the range of quantization error in the case of PCM system?
Delta square by 12.
The quantization noise power ma. Tell me the quantization error range.
Delta by 12.
Yes,
Plus delta by
yes,
2.
that is from minus
Delta
delta by 2 to
plus delta by
plus
2.
delta by 2. Very good. Okay, thank you. So what is the
Thank
range
you.
of quantization error in the case of PCM system? Minus delta by 2 to plus delta by 2. And there we got the quantization noise power as delta square by 12. Let us see how much you will get by using the delta modulation. Okay. Now please tell me what is the quantization error range in the case of delta modulation? In the case of delta modulation, the range is from minus delta to plus delta because our staircase waveform varies with a magnitude of either plus delta when the error is positive, varies by a factor of minus delta when the error is negative. So that's why what is the quantization error range in linear delta modulation? It is from minus delta to plus delta. But in the case of PCM, we took it as minus delta by 2 to plus delta by 2. If you take like this, that is B and B as delta and A as minus delta, what is the magnitude for a uniform distribution? 1 by B minus A, 1 by B minus A, where B is delta and A is minus delta. So 1 by delta minus of minus delta. So it will be 1 by 2 delta. But in the case of PCM, you got it as 2 by 2 delta. So we got the magnitude as 1 by delta in PCM. But here, because the magnitude range is from, error range is from minus delta to plus delta, you will get the magnitude as 1 by B minus A, where B is delta and A is minus delta. So 1 by delta minus of minus delta. So it will be 1 by 2 delta. Okay, so the same thing I told here. Let the quantization error be uniformly distributed from the interval minus delta to plus delta. If it is like that, then the probability distribution function B, let us represent it with same expression as we did in the case of PCM, Fe of E, F suffix E of E. Now the magnitude is equals to 1 by B minus A, where B is delta, A is minus delta. Okay, so it is 1 by 2 delta, for the error range from minus delta to plus delta. Now beyond that range, what is the magnitude? It is 0. What is the error? There is no error value beyond minus delta to plus delta. So error range from only minus delta to plus delta with uniform factor. Okay, so our probability distribution function is uniform because step size is fixed. Okay, so that's why we represented the equation Fe of E as 1 by 2 delta for error that range from minus delta to plus delta. Beyond that range, that is when error less than greater than delta and less than minus delta, it is equals to 0. Actually, it is less than minus delta. Okay, and for error greater than delta, it is also 0. When error range from minus delta to plus delta, you will get the magnitude as 1 by 2 delta. Okay, please remember this equation as 3. Now what is the definition for noise power? Ratio of, once again, mean square value of the noise signal divided by R. But how can you calculate the mean square value of the noise? How you did in the case of PCM? We did the same procedure as we are following here. That is integration minus infinite to plus infinite, error square into Fe of E dE. Okay. Now what is the error range in the case of PCM? Please kindly respond. How can you change the limits? In the case of delta modulation, The error range is from minus delta to plus delta. The range is from minus delta to plus delta. But in the case of PCM, the error range from minus delta by 2 to plus delta by 2. But here, because it makes use of 1-bit quantizer, the step size, the error, you can say, it has only the magnitude levels of minus delta to plus delta. Okay, so that's why what is the range here? You can change the limits from minus delta to plus delta, and during that period, what is the magnitude of the probability distribution function? What is the magnitude of the error at that time? It is 1 by 2 delta, because we calculated from the earlier slide as Fe of E is equal to 1 by 2 delta when the error range from minus delta to plus delta. Okay, so please calculate the mean square value. Integral minus infinite to plus infinite E square into Fe of E dE. What is Fe of E dE? From equation 3, you can replace Fe of E dE as 1 by 2 delta. Okay, so error square. So because 1 by delta, you can take it out outside the integration. So take 1 by 2 delta outside the integration. So 1 by 2 delta into, what is the integration of E square? What is the integration of E square? Please, one of you respond. What is the integration of E square? Deepika from lateral entry. Amma, please respond. Deepika.
E square x, ma'am.
Amma, enta? What is the integration?
E square x.
E square. What is the integration
X.
of E square dA?
E square dE.
E square dE. Or you can say x square dx. What is the integration?
E cube. E
Yes.
cube.
E cube by 3. You will get E cube by 3. So, and the limits are from minus delta to plus delta. Thank you. The limits are from minus delta to plus delta. Please substitute here. Please substitute the limits in E cube by 3. So that you will get delta cube by 3 plus delta cube by 3 inside the brackets. Okay. So you will get 2 delta cube by 3 inside the bracket and 1 by 2 delta outside the bracket. So the here 2 gets cancelled and you will get delta square by 3 and one of the delta gets cancelled from the numerator. So you will get delta square by 3. Now please tell me what is the quantization noise power in the case of delta modulation? Is Deepika there? Ma Deepika from lateral entry. Deepika from, okay, tell me how you got the quantization noise power in delta modulation? Deepika. Ma Deepika. Are you there or not? Okay. Ma Vikas from lateral entry. Are you there? Vikas. F2? F2. Okay, any other student kindly tell me what is the quantization noise power in the case of PCM system? What is the quantization noise power? How much you got in the case of PCM system?
minus delta by 2 to plus delta by 2.
Error is minus delta by 2 to plus delta by 2. See, I am asking the quantization noise power. So like this, we calculated the mean square noise power and we took R as 1 ohm. And finally, you got the quantization noise power for delta modulation as delta square by 3. And how much value you got it for PCM system?
Delta square by 12.
Yes, it is delta square by 12. So please remember, quantization error for PCM system is from minus delta by 2 to plus delta by 2. And quantization noise power is delta square by 12. Here quantization error range is from minus delta to plus delta. And in the case of delta modulation, quantization noise power is delta square by 3. Now please let us substitute these values in the case of SNR. So what is the definition for SNR? Ratio of signal power to noise power. Ratio of signal power to noise power. Okay. Now please let us assume, then please go through this figure here, shown here. So what is the noise power range here? It is from minus Fs to plus Fs, because it is a sampling frequency range. Okay. Let the cutoff frequency used at the DM receiver be W. So what is the cutoff frequency of filter, low pass filter used at the transmitter? It is plus or minus FM, plus or minus FM. For example, let us assume that the cutoff frequency used of the low pass filter used at the DM receiver be W. For some time, let us assume that W is not equal to FM. W is not equal to the frequency of the low pass filter used at the transmitter. Okay. Now what happens to the reconstruction filter? This filter allows only the part of the noise power that range from minus W to plus W. Okay. So from minus W to plus W, you can see the signal, that is a noise component. Okay. So what happens to the noise power then? Actually noise power is delta square by 3. For example, if W is not equal to FM, then W is not equal to FM, then quantization noise power is equals to W by Fs into the noise power obtained for the delta modulation. Noise power obtained from the delta modulation. So what is W here? W is the cutoff of, what is W? W is the cutoff of the low pass filter used at the DM receiver section. Please, for some time, please assume that this cutoff frequency is not equal to the cutoff of the low pass filter used at the transmitter. Then our signal component will exist, or you can say the noise component will exist only for the range of W. Okay. So we can define the noise power as W by Fs into the actual noise power value, because the noise content only exists for the W frequency. Noise exists only for the frequency range of W. Out of Fs, the signal, the noise component exists only for a range of W. So we represented W by Fs into the magnitude, original magnitude, that is delta square by 3. Now what happens to the output noise power when the low pass filter cutoff frequency of the DM receiver is not equal to that of transmitter, and if it is equal to W, so noise exists only for W range out of Fs. So that's why W by Fs into delta square by 3, where Fs is a sampling frequency that is reciprocal of the sampling time interval. Okay, so you can replace 1 by Fs as Ts. You can replace 1 by Fs as Ts. Now how you got a change? If the low pass filter cutoff frequency at the receiver section is W, then the noise power will change to W by Fs into delta square by 3. So if you take replace 1 by Fs as the reciprocal of sampling frequency as the sampling period. So you can replace W into Ts into delta square by 3. Take this as equation 6. Okay, this is a special condition where the cutoff of low pass filter at the receiver section is not equal to cutoff of the low pass filter at the transmitter section. Okay, now we know the definition for SNR. What is the expression for SNR? It is generally defined as the ratio of normalized signal power to normalized noise power. Okay, so we got the signal power as delta square by 8 pi square Fm square Ts square divided by the normalized noise power when low pass filter cutoff is not equal to the low pass filter cutoff at the transmitter section. So at the receiver and at the transmitter, the low pass filter cutoffs are not same, and at the receiver we have a cutoff of W. So that's why W into Ts into delta square by 3. Now here delta square gets cancelled. Okay, here delta square gets cancelled and one of Ts will also, so Ts you will get denominator, it's because it is in the denominator, you will get the SNR as 3 by 8 pi square W into Fm square into Ts cube. So this is the final expression for signal to noise ratio in the case of delta modulation. Okay, so with this almost all time up, we can stop the session here. Please wait for few minutes, I will take the attendance. I will continue the thing from the next class onwards. So once again we can discuss the SNR in the next class and then we can stop the session. Okay. So in the next class we can conclude the delta modulation. Okay. So any doubts in the today's class? Any doubts?